Hi, welcome to episode 3. Today I'm going to show you some of the preliminary get to know the technology work that I was doing on my function generator project. So the end goal for this project is for me to release an open source hardware function generator. Why? Well, I was looking on the internet and I noticed that there's pretty much two categories for function generators. There's either A, the extremely low-end, bare board, direct digital synthesis function generators that only allow you to control the frequency, not necessarily a very good reference clock, maybe for amplitude control, a potentiometer, and that's about it. Or you get the feature-packed products from professional level companies, Agilent or whatever, right? Where you can expect to spend a whole bunch of money to get one of these things and is well beyond the range of most hobbyists. So what I decided to do was, well, try to bridge the gap a little bit. Try to build something that has many of the features that you would find on these higher quality products, external triggering in, amplitude modulation, offset voltage control, phase adjustment, these sorts of things, while still being economically feasible to the hobbyist, and releasing it as open source hardware to, well, allow people to, maybe tinker with it, redesign it a little bit if they want to do whatever, right? So what we're going to do is we're going to take a look at some of the work that I was doing, which is, again, just when I was just trying to figure out how these DDS chips work, how I'm going to be able to get voltage offset and all these sorts of things actually working in the end. So again, this is what I was doing. Currently, I'm past this stage and I'm into the finishing the schematic. I'm pretty close on the schematic. There's a couple things that I need to change, but it's looking really good actually. And I've been spending many hours working on the bill of materials. Holy macaroni! Just I knew that it was going to be a lot of work to do that part, but I never knew quite how much it was going to be. But that's okay because it's going to be pretty good. Anyways, with all this, let's go over to back to the oscilloscope from last time, where I've got my function generator laid out, and let's take a look at what it can do. All right, so here we are over at the breadboard with my experimenting work here I was doing on my function generator. So let's go over what we've got, shall we? Alright, so I'm going to try to do my best to keep everything as much in focus as possible. So back here, this chip on this little breakout board here is the direct digital synthesis chip. It's analog devices chip. I believe it's the AD9833, I think it was, that I was experimenting with here. Let me try to get that out of the way there. So it's pretty good. It's not going to be the one that I'm going to use in the end. Some of the other models offer some additional functionality. Being able to set the output current is one of the features that the newer ones have, or not necessarily newer, but some of the higher models have. So there's a pin on it called, it's an adjustment pin, and then by changing the voltage across a resistor that you put on that pin, you change, well, the amount of current that comes out of it, and that current multiplied by some factor is the amount of current the output pin will send out. So the output pin on the one that I'm going to use is a current source, not a voltage source. So you have to then use a specific load resistor to then get the voltage that you want. So that's looking pretty good so far for digitally controllable amplitude in my new version. But anyways, this was me just testing, right? So what we've got here, this is our 10 megahertz reference clock, reference oscillator here. So it's not very, it's not very good. It's some really old 10 megahertz oscillator. It goes just absolutely everywhere. It's got terrible performance, but we'll see how I know that in just a little bit. But anyways, in there, right in there, we've got the microcontroller that I was using to test all these features out. And it is, I believe, a PIC 18F252, I think. I can't remember. Again, not going to be the one that I'm going to use in the final one. The final one's going to have a built-in USB, so we don't have to use the FTDI breakout and blah, blah, blah. Alright, so what we've got is we've got a whole bunch of pull-up resistors here for all the switches. This one's actually for the LED. This just lets me know that it is indeed plugged in and getting power. So we've got all of our switch buttons here. I'll show you guys what they do in a bit. And then we've got some other stuff over here. So let's talk about this first. One of the things that the microcontroller does is generates the offset voltage using pulse width modulation. So for a tutorial on how that works and how to figure out what your final smoothed out voltage is going to be, check out the video that Dave Jones did on the EV blog. He talks about pulse width modulation and whatnot, so I'm not going to go over that. In the final version, I'm going to be using a digital to analog converter instead, but I wanted to test out to see, well, to learn about PWM and also to just see that I can get correct offset voltages. Anyways, so what we do is we just smooth it out, and it comes into here, and then there's some analog stuff going on here. So what we do is we're basically just buffering it, amplifying it, and then non-inverting summing amplifier. There's some capacitors here. Alright, so there we go. Now we're in focus. So as you can see, I've got 20 picofarads of capacitance across this gain against the feedback resistor here, just to provide for some noise canceling and whatnot. This over here, this white wire, this is coming from my power supply over here. This is just a benchtop power supply. Well, it's a computer power supply that I converted into my kind of ghetto benchtop power supply, but it's providing the -5 volts for this. The +5 is coming from the USB there, so not to worry about that. So here's the LCD. What we're doing is it shows the frequency that it's outputting right now, and shows what kind it's outputting. If I switch to offset, or I can change the phase, it'll show that accordingly. But I'll show you guys more of that in a second. So we've got two probes set up also. We've got this one. This is right on the output of the DDS. And this probe right here, this is channel 2. This is on the output. This is on the output of the of all the op amps here after it's been summed with the offset voltage. And you know, appropriate gains applied and everything. So final output. So let's show off what some of the things we can do. So we've got 3 buttons here. We've got, this is offset voltage right now, this is frequency, this is phase. Phase isn't going to do much because of how poor this oscillator is, but proof of concept. What we've got is we've got this button here shifts which digit I'm selecting to the right, and then this is, oops, I just knocked that button out. And these two here increase and decrease the digit currently selected. So what we'll do is we'll go to frequency there, and I'll show you guys, see? So we can shift along, and we can increase it, and then it rolls over, and then it doesn't go down any further. I'm still hitting down. But if I go here and I hit down, you know, it does the math properly. So we've got 2 more buttons here. Oop, wires in the way. Got 2 more buttons here. This is sine output. This is triangle output. So I'll show you guys. Sine, triangle, great. And on the thing, triangle, sine. So right now the code, as you can see that little blip that happens. The code right now is updating all the registers in the DDS chip every single time you push a button. So the problem is that puts the DDS into reset mode every single time. So right now it's not a smooth transition. I'm gonna fix that for the final version, but no big deal right now. But, all right, let's take a look. So this higher trace here, this is the one coming out of the first channel. This is channel A, this is channel B. So this is it coming out of the DDS, this is it coming out of all the op amps. So we've got a slightly different scale here, as you can see. Channel 1 is 200 millivolts per div, and channel 2 is 500 millivolts per div, although they look about the same height. So what we're going to do, though, is we're just going to turn off, I'm just going to turn off channel 1. So this is our final output right now. So let's play with some of the things. So if I adjust the frequency, actually we'll just put that on measurement mode there too. And what we'll do is we'll just change these to channel 2. There we go. So we can see the mean, frequency, and peak to peak. Now I don't have amplitude adjustment right now because again this chip doesn't support that, so I can't show that. That wasn't part of my testing. But let's take a look at frequency there, right? See how it says it's floating around 1 kilohertz. See, it's changing a little bit. That's how I know that oscillator is really bad. That's not very high precision if it's changing by that much. But anyways, proof of concept. So let's change the frequency. So 2 kilohertz, 3 kilohertz, 4, right? DC. Let's go with 100 kilohertz. And then of course let's change the horizontal time base. So how about we change the offset, right? 1 volt offset. Oh, I'm sorry. This is actually not after all the parts. Whoopsie doodles. That's after the summing. Whoops, I was wondering why things were not cooperating there. 1 volt, there we go. 1 volt offset, 100 millivolts at a time. Look how nice that is. So right now it's set to 600, and the mean is 610. So, not bad for now. Not bad for some rounding errors and whatnot. It doesn't do negative right now because I just don't have that support. The next version will, by using a relay to switch the voltage into a inverting amplifier, but that's not included here right now. So let's turn that, say, to triangle, right? And 1 volt offset. Frequency, let's go with 1.1. Right, you can see it scroll up, and every time I hit it, again, it does that DC setting for a split second there. So let's take this to the extreme. Oops. This is pretty high. This is currently set to. There you go. That was, I accidentally added an extra 2 hertz. So right now we've got a whole bunch of artifacts because we're a little zoomed there. So if we zoom in far enough here, let's also increase that. So this is supposed to be triangle, right? We're kind of getting smoothed out a little bit and whatnot. So let's put this on sine actually, and let's zoom in further. Let's see, can we get this? We might be able to see this better on channel 1. Ah, there we go, because again, this is the unfiltered one. This will actually let me show the difference between the two. So channel 1 there, as you can see, let's put it on AC coupling actually. And where did the Oh, there we go. So sorry. For some reason I accidentally turned it off there. Okay. So anyways, what we've got is, this is channel 1, this smaller one here, and the bigger one is channel 2. So this one, remember, it's got that slight amount of filtering on it, right? While channel 1 does not. And you can see like these little steps, right? So what we'll do is we'll turn off channel 2 and we'll take a better look. And what we'll do is we'll just take one shot there. All right, wow, look at that. See? Step, step, step. That's why some filtering is important, because what it is that with the 10 megahertz clock, and we're outputting at 990 kilohertz, right? So we're at almost let's say 1 megahertz, right? You know, close enough. What we'll do is we'll put this on measure too, so we can see the little things. Let's put these on channel 1. Oops, there we go. It has no idea what the frequency is, of course. See, 994 kilohertz. All right, whatever. Let's zoom in. So continuing on, what we've got is we've got these steps because the output voltage in the DDS will only change every time the master clock ticks once. So at 1 megahertz, we're going to have 10. Our reference clock is going to be 10 times higher than that of our output frequency, which means that there will be 10 different steps in voltage per cycle, right? So this is about 1 right here. So, you know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? So pretty close there with the 10. And of course, we're not exactly on 1 megahertz. So yeah, pretty good. So you obviously want to reject that high frequency switching, which is why you then filter the output. Now, of course, theoretically, all you need is 2 points to define any individual frequency, right? You know, you have this point down here, this point up here, and then you filter, and what you'll get is you'll get the resultant sine wave. You know, if you guys know, of course, this is relevant to the Shannon-Nyquist theorem, where you need to have 2 points to define any one specific frequency. Although I'm going to talk about that more in another video where I talk about some DSP stuff. Some interesting things that people don't really know much about. But that's not today. Anyways, so we put back channel 2. As you can see, much nicer, much smoother, still a little bit of jitter. And then some, or not jitter, so a little bit of noise still, but not as big of a deal. So yeah, that's pretty much it for what I did when I was just experimenting and getting to know some of this technology. So I hope you all enjoyed episode 3. In the future, I plan on doing additional videos where I cover other aspects of the design process. Perhaps next time I will have the schematic, you know, more or less finalized, and we can go over at least revision A. You know, then there'll be other things. Maybe we'll talk about the layout itself, designing the case, which I've never done before, so that'll be a learning experience all on its own. But we'll see how things go, and hopefully some people will be interested in this, and I can sell some kits too. Anyways, see you guys next time. Bye.